Welcome back to The Explainer. If you've ever wondered how an electric vehicle seamlessly glides down the road, you are absolutely in the right place. Today, we're tracing the journey of power inside an EV powertrain. We're going to strip away all that dense academic jargon and uncover the actual physical reality of how stored chemical energy physically pushes you back in your seat.
Okay, let's dive into this with a really fundamental question. What actually happens when you press the accelerator in an electric car? In a traditional gas-powered car, you're opening a throttle, you're sparking a controlled explosion, moving pistons, the whole shebang. But in an EV, there's no combustion, there's no tailpipe, there's just this silent, immediate surge of torque. That magic, that instant response, is all the result of a highly orchestrated, blazing fast flow of electricity.
So here is our literal roadmap for the journey today. First, the anatomy of an EV. Second, the heart, which is the battery packs. Third, the brain, our power electronics. Fourth, the muscle, the electric motors. And finally, number 5, reversing flow with regenerative braking.
All right, let's look at the big picture before we zoom in. Part 1, Anatomy of an EV, Mapping the Territory.
And this brilliantly illustrates the overall architecture. Unlike a gas car that has this massive, heavy engine block shoved up front, the EV powertrain is completely modular. It's distributed. You can clearly spot the major hubs here. There's the massive traction battery pack, usually sitting flat along the floor. Then there's the inverter sitting nearby to translate the power, and the traction motor connected directly to the axles. This simplicity is exactly what makes electric platforms so incredibly flexible for designers.
If we strip that physical map down to its absolute basics, filtering out all the heavy mathematical modeling, it's really just a quick 4-step dance. Step 1, the battery acts as a direct current or DC energy source. Step 2, that power flows to the inverter, which translates it. Step 3, the translated power enters the motor, which acts as the physical muscle. And step 4, that mechanical power turns the transmission and the wheels. It is a wonderfully direct, high-speed path from stored energy right down to kinetic motion on the pavement.
And because that path is so beautifully direct, we hit a number that completely changes the automotive landscape. 85 to 90% efficiency. Think about that. When you press the pedal in an EV, up to 90% of the electrical energy from the grid actually goes into moving the car forward. Compare that to a traditional internal combustion engine, which sits around a, honestly, dismal 20 to 30% efficiency, just because it wastes so much energy as heat and mechanical friction. This massive efficiency gap, that is the real superpower of the EV powertrain.
Okay, moving to the energy source itself. Part 2, the heart, our battery packs.
This right here is the traction battery pack, and it's crucial to grasp the physical reality and scale of this thing. It's the heaviest, most expensive part of the whole car, often taking up the entire floor pan. But the most critical detail to remember about this pack, it stores energy strictly as direct current, or DC. Batteries literally cannot store alternating current, so every single drop of energy coming out of this giant pack is raw DC power.
Now, today, lithium-ion chemistry absolutely dominates the space. Why? Because it offers incredible energy density, typically somewhere between 100 and 250 watt-hours per kilogram. That packs a massive punch into a relatively small space. But, a battery pack isn't just a dumb box of cells. It relies entirely on a battery management system, or BMS, to monitor voltage and keep everything safe. On top of that, EVs have these incredibly complex thermal management networks. They use active coolant loops, refrigerant circuits, and electronic valves to route heating and cooling in real time. It basically acts as a life support system, preventing the cells from overheating when you're accelerating hard or plugging into a rapid fast charger.
Transitioning from the heart, we need something to manage all that flow. Part 3, the brain, or power electronics.
So, the crucial point is you can't just plug that raw DC battery directly into a modern electric traction motor. They literally speak different electrical languages. That's where the inverter comes in as the essential translator of the powertrain. It takes that flat, direct current from the battery and rapidly chops it up, converting it into precisely timed alternating current, or AC, that the motor actually needs to spin.
But the inverter is really just one piece of a larger power electronics suite. This suite is basically the intelligent control center of the car. You've got the traction inverter doing the heavy lifting of DC to AC conversion for the motor. Then you have a DC to DC converter, which is kind of like a transformer. It takes that terrifyingly high voltage from the main battery and steps it all the way down to a safe 12 volts to run your radio, your air conditioning, and your windows. Finally, you have the onboard charger, which does the exact reverse of the inverter. It takes AC power from your house grid and turns it into DC so the battery can actually store it.
Now, to make all this heavy-duty translation happen without the components just melting into a puddle of expensive plastic, the industry is shifting to some wild next-generation materials. Let's bust some jargon here. SiC and GaN. That's silicon carbide and gallium nitride. These are what we call wide bandgap semiconductors. Unlike your traditional silicon, these advanced materials let the electronics efficiently handle extreme voltages. We're talking upwards of 1200 volts and operate at way higher temperatures, which means the electronics can be smaller, lighter, and vastly more efficient. And for you, that directly translates to more driving range.
All right, let's put that translated energy to work. Part 4, the muscle, the electric motors.
So, a super common point of confusion is thinking, well, the battery provides DC power, so the motor must be a DC motor, right? Actually, scratch that. While early EVs definitely used brushed DC motors, modern manufacturers have overwhelmingly abandoned them for main traction. DC motors rely on physical brushes that constantly rub against a commutator. That creates friction, wear, heat, and electrical noise. By having the inverter translate the power first, modern EVs can use AC motors instead. And thankfully, AC motors are brushless. Zero physical contact means high efficiency, practically zero maintenance, and incredibly precise torque control.
But you know, not all AC motors are the same. The market right now is basically split into two main heavyweights. In one corner, we have the AC induction motor. These things are robust, they're cheaper to make, and crucially, they do not use rare earth magnets at all. They rely purely on electromagnetic induction to create a magnetic field. In the other corner, we have permanent magnet synchronous motors, or PMSMs. These actually embed strong permanent magnets directly into the spinning rotor. They offer the absolute highest efficiency and are super compact, but they do tie the manufacturer to the volatile supply chain of rare earth materials. Let's move to and see how this builds, because engineers are constantly pushing these boundaries. We are now seeing the emergence of axial flux motors, which have this weird flat pancake-like shape. They create a magnetic flux parallel to the axis, which delivers massive torque in a tiny, lightweight package. We're also seeing advances in reluctance motors, which ditch magnets entirely and use magnetic resistance to generate motion. It's this fascinating high-stakes arms race to increase efficiency while reducing our reliance on expensive metals.
Finally, let's look at a neat trick this whole system can do. Part 5, reversing flow with regenerative braking.
You've probably heard of one-pedal driving, right? This is powered by regenerative braking. Think about a gas car. When you step on the brakes, brake pads clamp down on a metal disc. All that forward momentum is literally just turned into heat and thrown away. But in an EV, the second you take your foot off the accelerator, the propulsion motor instantly transforms its role. It stops acting like a motor pushing the car and immediately starts acting like a generator.
Now, what's really interesting about this slide is seeing how our initial map plays completely backwards. The forward kinetic energy of the heavy, moving car physically turns the motor shaft. Because the motor is now in generator mode, that physical motion creates AC electrical power. The inverter steps in, intercepts that AC power, translates it back into DC, and shoves it safely back into the battery to be stored for later. You are literally recapturing energy that would otherwise just be wasted. This closed-loop system is exactly why EVs are just astonishingly efficient in stop-and-go city driving.
So today, we've traced that entire journey of power, breaking down the battery, the inverter, the motor, and how it all runs in reverse with regenerative braking. But you know, this technology isn't standing still. As we look to the horizon, I want to leave you with this to ponder. If current EVs are already operating at an incredible 90% efficiency, what happens in the next few years when solid-state batteries and advanced silicon carbide electronics push these powertrain efficiencies even closer to a perfect 100%? The journey of power is only going to get faster, cleaner, and more efficient. Thanks for joining me on this explainer, and keep learning.